Section 2 is multiplying and factoring with polynomials. Multiplying, we know what multiplying means. Factoring, we don't quite know what factoring means just yet, but I told you, like in the beginning of section 1, that factoring was actually a different way of saying the word divide. So in this section, we're using the distributive property to multiply a monomial times a polynomial. My hint is just watch for sign changes, and then remember, anytime you use the distributive property, combine like terms when you're done, but also watch for your sign changes and remember to add your exponents, coming straight out of section 1. So the distributive property says the term out front, this monomial right here is being multiplied into here and here and here. So we're going negative 3x squared times 7x squared. What do we get? Negative 21. But now I have x squared times x squared, which is what? It's x to the 4th. Yeah. So think back to chapter 7. When we were multiplying like bases, we had to add the exponents. In section 1, we were adding and subtracting like bases, basically. We were adding and subtracting like terms. The exponents stayed the same. But here, when we're multiplying again, we have to add the exponents. So you got to keep that kind of straight. All right, next one. We have negative 3x squared times negative x. What do we get? Positive 3x to the what? 3rd. Because that's x squared times x, which is x to the 3rd. And then for my last one, negative 12x squared. That's an x squared, and there's no x involved in that last term, so it just stays x squared. Notice that these are written in standard form. It's the highest power, or the highest degree, down to the lowest degree. 4th degree term, 3rd degree term, 2nd degree term. This is a good answer here. Okay, my second one, what should I do? Well, we'll distribute. Okay, so what do we get for the first one? Negative 20. A to the 6th. Good. Is it 10 or negative 10? So plus 10, a to the 3rd, and then 5 times 7 is 35. A squared. So basically what's happening on these is you're multiplying the numbers together and then you're adding the exponents on the variables. A to the 2nd times a to the 4th is a to the 6th. So just keep that straight. Go ahead and try that last one. What do we get? Negative 18 d to the 7th plus 12 d to the 6th. Good. Oops. See, I wrote 3rd. 6th. And then 6d to the 4th, because that's a d to the 1st right there. So d to the 3rd times d to the 1st is d to the 4th. And then minus 54d to the 3rd. There you go. And again, it's in standard form. We have the 7th degree term, then the 6th degree term, there's no 5th degree term, then the 4th degree term, then the 3rd degree term, and then there's nothing else. So that's the correct answer right there. All right, let's try this again, because in the last section we had some trouble coming up with what the most important thing was on the page. Probably the most important thing on this page is what? Is there an or up there? No, I don't see an or.
The dash between like terms.
Yeah.
No. Combine like terms, of course. Always, when you distribute, I've been saying that all year, since August even. We learned the distributive property back in August. And I've been saying that ever since. When you distribute, Always look for like terms to combine. So, on a problem like this, really complicated looking problem, notice right here, first of all, you have what going on right there? What are we going to have to do there? Distribute, yeah. And then what do we have going on right here? Distribute. So we're going to distribute twice. And then once we're done, we'll probably have some like terms to combine. Okay? Now there's one more thing that I want to point out. That minus sign right there. Do a keep, change on that. That's going to help you remember that that's actually a negative 5. So write plus and then negative 5. So that when you distribute that negative 5 in, you remember that it's actually a negative 5 that you're distributing. So let's take out that first set of stuff. We have a monomial times a what? A what? How many terms are there in here? 2. So it's a binomial. Good. So we have 2p times negative 4p squared. What do we get? Negative 8p to the third plus 10p squared. All right, now we did a keep, change on that minus sign to make it a plus a negative 5 that we distributed. What do we get? Negative 10p squared. And then what? What? Negative 100? Okay, minus 100. Now what? No, all we did was do a keep, change right here on this minus 5. We turned it into a plus and negative 5. So that when we distribute, we know that that's a negative 5 that we're distributing in. Okay? In section 1, if there wasn't a 5 there, then we'd basically just be subtracting 2 polynomials. And that's when we did keep, change everything. But in this case, it's just this front number right here. So now we're going to combine like terms. Do we have any like terms to combine? Which terms? Yeah, notice that these are like terms. They have a p squared here and a p squared here. So those will combine. What about this negative 8p to the third? No, that one's on its own. So we're just going to write that one down. Negative 8p to the third. And that takes care of that front term. Now, 10p squared minus 10p squared. What is 10 minus 10? 0. So you get 0p squared, which is what? It's 0. So that term actually completely disappears. They add to 0. And I'm left with the minus 100. So when I combine like terms, my answer is just negative 8p to the third minus 100. And I'm done. All right, talk me through the next one. Distribute that first one. Yes, I know what you're saying. We'll get there when we get there. Let's distribute here. 15x squared plus 6x minus 12. So you want to change that? Okay. Now what? So that's just negative x times a positive 7x squared, which becomes negative. So I'm going to write minus 7x to the third cubed. Then what? Plus negative 2x squared, right? Plus negative is just straight minus. A negative times a positive is negative. So I just write minus and then 2x squared. And then what? Plus 3. Just 3? Don't forget your x at the end. Now what? All right, combine like terms. Start with the highest degree term, which is what? All right, we have an x squared term, so 15x squared. Well, there's a negative 7x to the third right there. So start with that one. That's the highest term. What do I write down? Negative 7x to the third. And now that term's gone. Now we can go to the x squared term. Do we have like terms to combine with that one? Yeah, what do we get? Yeah, that's 13. So what do I write? Plus 13x to the what? Squared. We're combining like terms. The variable and the exponents don't change. We had 15x squared. We took away 2x squared. And we wound up with 13x squared. Then what? 6x plus 3x plus 9x minus 12. There you go. X to the third, x squared, x, and then that negative 12, x to the 0. There's your answer. So be careful. If you're combining like terms, when you're combining them, the variables and the exponents do not change. When you're multiplying, that's when exponents change. So let's take a look at this third one, because this one's different than what you've seen so far, even in this entire chapter so far. We're still distributing here. Once you see what that first term turns into, I think probably you'll be fine with the rest of it. So what does that first term turn into? 150. That's t times y to the third, t to the fifth. So what do we get? Y to the third, t to the sixth. What happened? The t multiplied to the t to the fifth and became t to the sixth. There was no y to multiply in here, so the y to the third stayed the same. The t got sent to that. Okay? And then it added the exponent. So it's not a big deal. You're still multiplying the numbers together. You're still multiplying the letters together. But you're only multiplying the letters that are the same together. So what's my next term going to be? Very good. What happens next? Do a little keep change here to not get confused with that minus sign. And what do we get next? Negative 2y to the second this time, because we're multiplying y times y, which is y squared. Nothing happened to that t squared, so it stays t squared. Very good. And what's the last one going to be? So minus 8y to the third. Very good. Now what? Combine like terms if we have any. Do we have any? A couple head nods, yes. Which terms are like terms? So remember the rules for combining like terms. The variables and the exponents have to match. So in this term I have y and t. I have y and t here. Are those like terms? No, why not? Yeah, the exponents don't match. This is y to the third, t to the sixth. This one is y squared, t squared. They're not like terms. But over here, y squared, t squared, I have a y squared, t squared. These two right here are like terms. And then this last one is just y to the third. Is that a like term with anything? No. If it had a t to the sixth at the end like this one did, then yeah, sure. But those are not like terms. So this one is not a like term with anything. I'm going to rewrite it. 150, y to the third, t to the sixth. Then I do have like terms here. What do I get? Yep. Plus 73, y to the second, t to the second. The variables and the exponents stay the same when you're combining like terms. And then I only have one term left, minus 8y to the third. Notice that the degrees of these terms have been written in standard form. We're in descending order. What's the degree of that term? How do you find the degree of a term? You add the exponents together, yeah. So what's the degree of this term? 9. And the degree of this term is?
4.
And the degree of this term is? And they're written from left to right, highest to lowest. So this actually is standard form here. Even though there's lots of letters and lots of exponents, that's the correct standard form. So everything that we've done so far is present in numbers 9 through 14 all. That's 6 problems or so. Have at it. The next part of this section is factoring. So before we get into actually factoring stuff, we need to review how to do some of this sort of thing. You've learned how to do this before, somewhere along the way, 6th grade, maybe 7th grade. Writing a prime factorization tree, or some people use a cake, or some people just can do it in their head. So I'll show you how to do this using the tree, and then I'll show you how to do it using the cake, and then I'm going to tell you that I hope that very, very quickly you learn how to do this in your head. So here we go. This is an example that's not on this page. I want to find the prime factorization of the number 48. The prime factorization means you're writing 48 as a product of prime numbers, all being multiplied together to give you 48 as its answer. So to do that, what you want to do is, here's the tree. Split 48 into a prime number times something. And it's always going to be the smallest prime number that you can think of that goes into 48. Is 6 a prime number? No. Okay, so what is a prime number?
It can only be multiplied by 1 in itself.
Oh, only be divided by 1 in itself. Yeah. So the first prime number that we have is what? 2. 1 is actually not a prime number. The 1 is defined as not prime, okay? There's a reason for that. If you ask me a little bit later, I'll tell you why. But 1 is not prime, 2 is prime, because only 1 times 2 gives you 2. 2 is only divisible by 1 and itself. So 2 is my first prime number. Does 2 go into 48? Yes. How many times? 24. So I'm going to write 2 and then 24. 2 is already prime, so that side of the tree is done. 24, is that prime? No. So I'm going to branch out again. And what is the smallest prime number that goes into 24? 2 again. So 2 times what gives me 24? 12. Is 12 prime? Nope. So I can split 12 into what? 2 and 6. Is 6 prime? Nope. I can split 6 into 2 and 3. Is 3 prime? Yes. So then I'm done. That's the prime factorization tree for 48. So the answer for this 48 would be 2. I just take 2 times 2 times 2 times 2 times 3. Just read them right off here. Because 2 times 24 is 48. But 24 turns into 2 times 12. So it'll be 2 times 2 times 12. But 12 turns into 2 times 6. So that's 2 times 2 times 2 times 6. But 6 turns into 2 times 3. So it's 2 times 2 times 2 times 2 times 3. 2 times 2 times 2 times 2 times 3 is 48. There's another way to do this, which is a little bit simpler than the tree. It takes up less space. So maybe you've seen this way. I'm going to take 48 again. But this time, I'm going to do like upside down division, basically. It winds up looking like a cake with lots of tiers to it. So somebody will say the cake way of doing the prime factorization, like next year maybe. So it's done the same way. What's the smallest prime number that goes into 48? 2. And then 2 times what gives me 48? Or you could think 48 divided by 2 is 24. if you look at that as an upside down division problem. Okay? Now you divide again. What's my smallest prime number this time? 2. And I get 12. And then I divide again, and it's 2, and I get 6. Divide again, 2 and 3. We wind up with exactly the same look as over here. It's still 2 times 2 times 2 times 2 times 3. So both of these methods get you to the prime factorization of 48. Okay? So let me do another one. Let's try 15. I want to find the prime factorization of 15. Whichever method you prefer is fine with me. What's the smallest prime number that goes into 15? 3 times what? 5. And then we're done. That's as far as we had to go. So 3 times 5 is the prime factorization of 15. Now let me get rid of that. And let's make this instead negative 15. In order to do this, the first thing we have to do is kind of divide out a negative 1. So I'm going to take out that negative 1 right away, which will leave me with 15. And then I can do the 3 and 5. So the prime factorization of negative 15 becomes negative 1 times 3 times 5. That's how we handle a negative sign. So if this was actually negative 48 up here, before I did this, I would split that negative 1 out, and then I'd have negative 1 times 48, and then I could continue with the tree or with the cake. Okay? Now that comes up because right away, the first example that we have is factor negative 20x to the third y squared completely. So I need to erase some of this stuff to make more room. Let me go ahead and do that. Okay, so I want to find the prime factorization of negative 20. So first thing I'm going to do is set up the negative 20. And when we're doing it this way, I prefer the cake way, not the tree way. What's the first thing I got to do? The negative 1. Got to make that negative 20 a positive 20. So I wind up with 20. What was that? 2 and 10. And then 2 and 5. And then 5's prime, so we're done. Now we've got to write that out. So it's negative 1 times 2 times 2 times 5. But we also have this x to the third y squared being multiplied on. Yes, x to the third just means x times itself 3 times. So I write times x times x times x times y times y. And you're done. That's the answer. What's that? What's the point? You'll see in a little bit. We just have to remember, hopefully you've seen this before, but if not, then you need to just remember that this is how we do it, or learn that this is what we're supposed to do, because in a little while we're going to be finding the greatest common factor of certain numbers. And if you remember back when you learned how to do this or this, that's how you found the greatest common factor. So, what should we do with 34x to the fourth y to the third? The directions say to factor completely. All right? Factoring completely means we're going to wind up with this sort of look to it. So, what should we do? Do the division thing. So 34, and we see that 34 is even, so 2 definitely goes into 34. How many times? No. 17. And do we have any more numbers that we can do? No, 17 is prime, so that's it. Now what do I do? 2 times 17 times, and then times, and there's your answer. So a couple of reminders on how you can tell if something is divisible by a certain number or not. First of all, for 2, it's easy to tell if a number is divisible by 2 because it'll be even. So if it's divisible by 5, the number will end in a 5 or a 0. If a number is divisible by 3, what can you do to check to see if it's divisible by 3? Yes, add up all the digits that you see. So like, for example, 48. 48 is divisible by 3. If you don't know that off the top of your head, take the 4 and the 8 and add them together and you get what? 12. And if that number is divisible by 3, then the original number is divisible by 3. So therefore, 12 is divisible by 3, which means that 48 is as well. Okay? It always works. And there are other ways that you can tell if a number is divisible by a certain number. But those are the important ones, 2, 3, and 5. Those are the ones you really need to know, okay? So is 34 divisible by 3? No, because I take 3 and 4, add them together, and I get 7. 7 is not divisible by 3, so therefore 34 is not divisible by 3. And when we found the prime factorization, you can tell it's not divisible by 3. All right, let's go ahead and try to do this last one here. What should we do first? Yeah, we got to find the prime factorization of negative 52. So I have the 52 here, and it's negative. And the first thing I got to do is the negative 1. And then now I have the positive 52. And now we're ready to go. So what's my first move? 2, which gives me 26. And that's not prime. 2 and 13. And 13 is prime, so that's done. So what's my answer? There you go. Here's why we need to know how to do what we just did. It's because now we're going to find the greatest common factor, the GCF. You'll hear me say GCF a lot from here on out for the rest of the year. We're going to be using GCF quite a bit. So, to find the GCF of 2 monomials, the greatest common factor of 2 monomials, which means basically the biggest thing that is a common factor of, which means that it's the biggest thing I can multiply into something else to wind up with what I'm looking at. First of all, factor each monomial completely. That's what we were just doing. Then, circle the common factors in each monomial, and you'll see what I mean by that here in a second. And then multiply the circled factors back together, and that is the GCF for those monomials. It's really a fairly straightforward thing once you see how these steps work. So the first thing we want to do for this problem is factor each monomial completely. Notice that there are 2 monomials here, that one and that one, 12a squared b squared c, 18ab to the third. We want to factor those completely. So I got to factor 12 completely first. 12, what's my first prime number? 2, and then I'm left with, yep, and then that becomes 2 and 3. I also got to factor 18 completely. So I'll do that now. What's my first prime number there? 2, and I'm left with 9, and then 3 and 3. Okay, so now write them out in completely factored form. For 12a squared b squared c, I have 2 times 3 times a times b times b times c. For 18ab to the third, I have 2 times 3 times a times b times b times b. So that's step 1. Step 2 now says circle the common factors of each. So we're going to look at the 2 completely factored forms for those 2 monomials and start circling pairs. We're finding matches. So what I do to do that is I just pick one. I don't look at both. I look at the top one. And I look at that first one into 2. Then I go to the bottom one and say, do I have any 2s down at the bottom? It's kind of like go fish. I do. I have a 2 right there. So I circle them. Those are a pair. Now I'm just going to work my way across this top one here. And when I get all the way done, I'll have found all of my pairs that match. So then I go to the next term, a 2. Do I have another 2 that's not circled down here? No. So that 2 doesn't work. What about that 3? Do I have a 3 down in the bottom one? Yes. So I circle that 3 and that 3. What about A? Do I have an A in the bottom one? Yeah, right there. So I'm going to circle that A and that A. What about that A? Do I have another uncircled A in the bottom? No, I don't. So I'm going to skip that one. What about that B? Yes, I do. I have a B and a B. What about that B? Yes, I have a B and a B. What about C? No, there is no C down here. And now because I looked at only the top one and made matches with just the top one, I don't have to worry about anything else. I made it all the way across and I've circled all the pairs. Even though I got another B down here, it doesn't matter because there's not another uncircled B here. Just look at the top one and circle your matches all the way across, and then when you're done, you're done. Then multiply the circled factors back together. Again, just on the top one, we have a 2 times 3 times A times B times B. That is the GCF. So 2 times 3 times A times B times B is the GCF. But then we multiply all those back together. 2 times 3 is 6. A, B squared. There's your GCF. So with practice, you guys probably will be able to skip writing down this right here very soon. In fact, you probably won't ever do it again. I probably won't ever do it again. You'll be able to go straight from here to here. Because really, it's just 2 times 3, which is 6, A, and then B times B, which is B squared. With more practice, you probably will be able to get away from even doing the completely factored form. And you'll be able to just go straight to the GCF. And that's my goal, is to get you guys all, at this point, to be able to go straight from this right here to this right here without having to do all this extra work. You'll be able to fairly soon. Trust me. All right, let's take a look at this problem. What do we do first? There you go. Remember, I said at the beginning of the chapter, I'm going to want you guys to use the vocabulary as much as you possibly can. So, factor completely. 6 turns into what? 2 times 3, and then that's it. That's as far as we can go. So we have 2 times 3 times what? Good? And then what do we do? Okay, so 18. 2 and 9, and then 3 and 3. So that gives me okay, and now what do we do? Circle your pairs. Yeah, circle the common factors. The 2's, the 3's, the y's, and that's it. Working your way right across the top one. So then what's the GCF? 6y, and that is it. There's your answer. All right, see if we can do the last one. So for the last one, what does that first term turn into? 11 times A times B is correct. And what does the second term turn into? 21 is not prime. 3 times 7 times A times B times B. All right, now what would we do? Common factors are, start at 11. There is no 11 down here. Move to the A. There is an A here. Move to the next A. There's no other A here. Move to the B. There is a B there. And I'm done with that top one, which means I'm done completely, which means my greatest common factor is AB. I didn't circle the 11. It was just the AB. This is where it gets fun. Finding the greatest common factor of more than just two monomials. To do this, it's the exact same thing as with two monomials, but now the common factors need to appear in every term. Whether I have 3 terms or 104 terms, I have to have a common factor in every single one of them before I can call it a common factor. So I need to turn all of these into completely factored form. What does 25 become? 5 times 5 times, good. And what does 45 turn into? So 9 times 5 is right, but 9 is not prime. So it's actually 5 times 3 times 3 times x times x. Good. Make sure that those numbers are actually prime, otherwise this won't work. What does 65 turn into? 5 and 13 is right. So 5 times 13 times x times x. And now we're looking for factors that appear in all 3. The 5 definitely does. This 5 does not. X? Yes. The next x? Yes. The next x? No. So that's it, which means my GCF here is 5x squared. Very good. Go ahead and do the last one.